Chemistry. It's not just bubbling beakers and complex equations, it's the science of the everyday. From the air we breathe to the food we eat, chemistry is the cosmic dance of atoms and molecules. Understanding chemistry unlocks the secrets of our universe, revealing the elegant rules governing matter's behavior. In this grand cosmic ballet, understanding how substances dissolve and interact is crucial. This brings us to the fascinating world of compounds and their solubility. Imagine the periodic table as a cosmic address system. Each element, like hydrogen or oxygen, represents a unique type of atom. These atoms, the fundamental building blocks of matter, rarely exist in isolation. They prefer to mingle, forming bonds with other atoms. This cosmic dance of connection gives rise to compounds, substances formed by the chemical combination of two or more elements. There are two major types of compounds, covalent and ionic. Understanding their differences is key to unraveling the mysteries of solubility. These compounds, with their unique bonding characteristics, dictate how substances interact with solvents, leading to the formation of solutions. Imagine two atoms, each yearning for a stable existence. They are like partners in a dance, moving closer to find balance and harmony. They achieve this stability by sharing electrons, the negatively charged particles orbiting an atom's nucleus. These electrons are like tiny messengers, carrying the promise of stability. This sharing of electrons is the essence of a covalent bond. It's a mutual agreement, a handshake that binds the atoms together. Water, the elixir of life, exemplifies this type of bond. Without these bonds, water wouldn't have the properties that make it so vital to life on Earth. Two hydrogen atoms share their electrons with an oxygen atom, creating the H2O molecule. This simple yet profound interaction is what makes water so unique. This sharing creates a stable arrangement, holding the atoms together. The stability of water molecules is crucial for countless biological processes. Covalent bonds are the glue that holds together many familiar substances. These bonds are everywhere. Sugar, for instance, is a complex network of carbon, hydrogen, and oxygen atoms held together by covalent bonds. These bonds give sugar its structure and sweetness. These bonds are relatively strong, making covalent compounds generally less likely to dissolve in water compared to their ionic counterparts. This strength is what makes covalent compounds so essential in the natural world and in our daily lives. In the realm of chemistry, opposites attract. Ionic bonds arise from the electrostatic attraction between oppositely charged ions. These ions, atoms that have gained or lost electrons, form when one atom donates an electron to another. This transfer creates ions with opposite charges, positive, cation, and negative, anion, which are then drawn to each other. Table salt, NaCl, perfectly illustrates this concept. Sodium, Na, readily donates an electron to chlorine, Cl, forming Na+ and Cl ions. These oppositely charged ions attract each other, forming a strong ionic bond that results in the cubic crystal structure of table salt. This electrostatic attraction is what makes ionic compounds particularly soluble in water. Dissolving the mystery solutions and solubility. How do substances interact and dissolve to form solutions? Imagine stirring a spoonful of sugar into your morning coffee. This everyday action is a perfect example of solubility in action. The sugar crystals seem to vanish, but they haven't disappeared. Instead, they have undergone a process that makes them invisible to the naked eye. They've dissolved, becoming uniformly dispersed throughout the coffee. This means that the sugar molecules are now evenly distributed in the liquid. This magical transformation is the essence of solubility. It's a process that occurs at the molecular level, where the solute particles interact with the solvent particles. A solution forms when one substance, the solute, dissolves evenly into another substance, the solvent. This interaction is crucial for creating a uniform mixture. The resulting mixture, the solution, is homogeneous, meaning its composition is uniform throughout. Every part of the solution has the same ratio of solute to solvent. In our coffee example, sugar is the solute, water is the solvent, and the sweetened coffee is the solution. This simple example helps us understand the basic principles of solubility. Solubility is the ability of a solute to dissolve in a particular solvent at a specific temperature. Different substances have different solubility levels. The solubility of a substance depends on factors like the nature of the solute and the solvent, temperature, and pressure. These factors can significantly influence how well a solute dissolves. Understanding these factors helps us predict whether a substance will dissolve and to what extent. This knowledge is essential in fields ranging from chemistry to cooking, and even in medicine. Aqueous solutions. Water, the universal solvent. Water, the lifeblood of our planet, is also a remarkable solvent. Its polar nature, arising from the uneven sharing of electrons between hydrogen and oxygen atoms, allows it to dissolve a wide range of substances. This ability to dissolve many substances earns water the title of universal solvent. In an aqueous solution, water is the solvent. These solutions are ubiquitous in nature and essential for life. From the salty oceans to the fluids within our bodies, aqueous solutions play a vital role in countless chemical and biological processes. Strong electrolytes. Bright lights, big conductivity. Imagine a light bulb connected to a battery by a circuit. Now, introduce a solution into the circuit. If the bulb lights up brightly, the solution contains strong electrolytes. These substances, when dissolved in water, dissociate completely into ions, facilitating the flow of electrical current. Strong electrolytes are like efficient conductors of electricity in solution. They include strong acids like hydrochloric acid, strong bases like sodium hydroxide, and soluble salts like sodium chloride. These substances, when dissolved in water, readily form ions, allowing the solution to conduct electricity efficiently. Weak electrolytes, dimming the lights. If the light bulb in our experiment glows dimly, the solution contains weak electrolytes. These substances only partially ionize in solution, resulting in a limited flow of electrical current. They are like hesitant dancers, only partially entering the dance floor of ionization. Weak acids like acetic acid, also known as CH3-CoO, and weak bases like ammonia, NH3, are examples of weak electrolytes. These substances maintain some of their molecular integrity in solution, resulting in a lower concentration of free ions and therefore weaker conductivity. Non-electrolytes, no flow, no glow. What if the light bulb remains unlit? This indicates the presence of non-electrolytes. These substances dissolve in water but do not ionize. They are like spectators at a dance, present but not participating. Sugar and alcohol are prime examples of non-electrolytes. These substances, when dissolved in water, do not form ions. They remain as intact molecules within the solution, hindering the flow of electrical current. This lack of ionization makes them non-conductors of electricity. Solubility guidelines, predicting the outcome. Chemists have developed solubility guidelines, a set of rules, to predict whether an ionic compound will dissolve in water. These guidelines, often presented in a table format, consider the cation and anion of the ionic compound to determine its solubility. For instance, all nitrates, No3, are soluble in water regardless of the cation. Similarly, most chlorides, Cl, are soluble except for those combined with silver, Ag+, lead, Pb2+, or mercury, Hg2+. These guidelines provide a useful framework for predicting the outcome of mixing different ionic compounds in water. The significance of solubility, from chemistry labs to our daily lives. Real examples in action. Understanding solubility is not just for chemists in labs, it's a concept that permeates various aspects of our daily existence. It's crucial in our daily lives, affecting everything to the food we eat. From dissolving sugar in our coffee to the medications we take, solubility plays a critical role. When you stir sugar into your morning coffee, you're witnessing solubility in action. It influences the taste of our food, ensuring that flavors are evenly distributed and enjoyable. The effectiveness of our medicines depends on how well they dissolve in our bodies, making solubility a key factor in healthcare. And even the health of our environment is impacted by solubility. Pollutants dissolve in water, affecting ecosystems and human health. Solubility is central to environmental processes, influencing how substances interact in nature. The dissolution of gases like oxygen in water is essential for aquatic life. Fish and other marine organisms rely on dissolved oxygen to survive. Understanding the solubility of pollutants helps us develop strategies for cleaning up contaminated water sources. This knowledge is vital for maintaining clean and safe water supplies. In essence, solubility is a fundamental concept that bridges the microscopic world of atoms and molecules to the macroscopic world we experience every day. It connects the unseen chemical interactions to the tangible effects we observe in our surroundings. By understanding solubility, we can better appreciate the intricate balance of our natural world and make informed decisions to protect it. If you found this video helpful, please like, share, and subscribe to the channel for more academic content. Have a nice night and good night.